Welcome to the first installment of the Academy Lecture Series, Aerodynamic Decelerator Systems. My name is Al Wowski, and I am an industry member of the Flight Mechanics Technical Discipline Team. I am also the Director of Engineering Operations at Pioneer Aerospace Corporation, and have been designing aerodynamic decelerators for NASA for over 2 decades. This module is about the origin of aerodynamic decelerator systems and their heritage use. This lecture series is intended as an informal update to the recommended reading. It is not intended to replace the AIAA Aerodynamic Decelerator Systems short course, which is held every other year. It's simply not possible to provide sufficient detail in these short video modules. And the group of industry and NASA personnel who run the AIAA short course provide a much broader experience base than a single person can provide. Note the disclaimer, and that the intent is to keep all modules free of ITAR restrictions. However, this may be difficult when providing details on modern projects and current numeric modeling techniques. Aerodynamic Decelerator Systems, or ADS, are typically the D in EDL. The example shown from a '69 NASA press release is typical for their use and demonstrates a fairly common application and types. Note the drag chute, or forward bay cover decelerator, used to prevent cover recontact. The drogues, used for initial speed, dynamic pressure reduction, and trajectory alteration. The pilot parachutes used to deploy the main canopies, and the main canopies used to set the terminal descent for final water entry conditions. If one considers an object that uses atmospheric drag to slow one's descent is a decelerator, then the origin of ADS can be traced to legends from ancient China. There is a legend that Shun, son of Emperor Go-Shu, used 2 bamboo hats to slow his fall from the top of a building that his father had set fire to in an attempt to kill him. A couple of millennia later, records from the Han Emperor courts describe acrobats entertaining the nobility by using something between a bamboo hat and an umbrella to survive jumps from great heights. There are also legends concerning a thief who stole a gold rooster off the spire of a temple in 1180 and got away by leaping from the top with a large umbrella to slow his descent. The earliest record of a decelerator that was actually intended to be used for the explicit purpose of slowing someone's descent is from Da Vinci's famous notebooks. Although there is no record of Da Vinci ever attempting to test his device, a skydiver did just that in 2000. It performed quite well, was very stable, but was also at the mercy of the prevailing wind and was quite bulky at a couple of 100 pounds. Parachutes in the form of umbrellas came back into fashion as entertainment in the late 1700s, and prior to inventing the balloon, the Montgolfiers were one of those developing refined versions of these devices. Of course, with the invention of the balloon, there became the actual need for these devices as a means of rescue, and the first recorded emergency use belongs to the Polish aeronaut Yordaki Kuparento when he jumped from his burning balloon in 1808. Note that up to the late 1800s, all parachutes were based on the umbrella, with some portion comprised of rigid structure. This changed with Thomas Baldwin. Captain Tom, as he liked to be called, is best known as the father of the American dirigible. But before he entered the Army Air Service, he was an entertainer balloonist and invented the first fully flexible parachute in 1887. He would make money by jumping his device and charging $1 a foot of descent. With the advent of heavier-than-air flight and using Captain Tom's parachute design, inventors then developed seat, chest, and backpack-style parachutes for emergency escape from aircraft. These parachutes were attached to a hard point in the aircraft cockpit, and the air crew were required to jump from the disabled vehicle with the canopy deploying as they fell away from it, also called a static line deployment technique. The image at left clearly indicates a typical problem with the static line deployment technique, made even more treacherous by the fact that the aircraft would most likely be in an uncontrollable state during a warfare situation. Floyd Smith invented a ripcord-style pack that could allow aircrew to jump clear from a stricken craft before deploying the parachute. He was a member of an Army team that was conducting a fly-off of various emergency parachutes and put his own design up for competition. Many stories exist for why he did not jump his own design, but whatever the reason, Leslie Irvin became the first person to jump a ripcord-style parachute on 24 April 1919. Floyd Smith's Type A parachute then became standard equipment for the Army Air Forces. As a side note, the current world leaders in engineered aerodynamic decelerator systems can trace their roots back to these two men. Leslie Irvin started Irvin Airshoot, which changed names over the ensuing years and is now known as Airborne Systems North America. After getting out of the Army, Floyd Smith got together with Lyman Ford, and they started Pioneer Parachute, with Floyd as chief engineer. After changing its name over the last three-quarters of a century, Lyman and Floyd's company is now called Pioneer Aerospace Corporation. With the success of aircraft in World War I and the continued development of the packed parachute, it did not take long for military strategists to come up with new ideas for their use. This image is of the first recorded American paratrooper training at Brooks Field in Texas. Using single personnel parachutes to airdrop small supplies in remote areas began in the early 20s. However, it took some time before heavy equipment airdrop was attempted. The first recorded American heavy equipment airdrop occurred in 1941. It landed an 800-pound artillery gun and ushered in the era of air delivery using a cluster of personnel canopies, which may have looked similar to this modern image. Up until about the midpoint of World War II, parachute development consisted mostly of come up with an idea, cut it, sew it, and fly it, all very much just trial and error. There are few, if any, documents associated with the why regarding the operation of decelerators. This changed in Britain and Germany with dedicated groups of scientists and engineers looking for an edge in the World War. Helmut Heinrich and Theo Kanaki were two German decelerator engineers that were encouraged to come to America at the end of World War II as part of Operation Paperclip. They were to American decelerator development as von Braun was to American rocketry. With the advent of faster jet aircraft, the ability to jump clear became impossible, and the ejection seat was developed. German test pilot Helmut Schenk was testing a Heinkel HE-280 jet fighter when his plane iced up, and he was unable to restart his engines. He jettisoned the canopy and activated the seat powered by compressed gas, becoming the first successful ejection seat user. Ejection seats are now standard equipment on all fighter aircraft. The heyday of aerospace development in the 50s and 60s was closely matched by decelerator development. As aircraft and missiles were getting faster and higher, so too were the needs for deceleration. For instance, in the 1940s, 40,000 feet was considered high altitude, but by 1960, Joe Kittinger leaped from a balloon gondola at 102,800 feet and landed safely with the aid of flexible decelerators. Speed was all the rage during this period, with applications in atmospheric sounding experiments, ordnance devices, high-speed aircraft escape, and human spacecraft recovery. Mid-air retrieval was developed for the recovery of the first articles from space, which were reconnaissance film canisters, as part of the Corona program. This 1967 image of a 1,600-kilogram UAV capture can be considered typical. Note that the Russians recovered live animals from space just a few days after Discoverer 14. The obvious connection between human recovery from space and human recovery from high-speed aircraft is made with the Mercury capsule system, which used a ring-sail parachute that was originally developed for personnel use. Gemini attempted the use of a steerable parasail and retro rockets for land landing. Unfortunately, the technology was not sufficiently developed to meet the program schedule and had to be abandoned for a scaled Mercury-type system. Ejection seats were used as a backup. Apollo expanded the Mercury and Gemini systems with a cluster of ring-sail decelerators as its landing system. The shuttle incorporated a landing decelerator in the 90s to reduce wear on its landing gear brakes. Large clustered decelerators are now common for airdrop of cargo, including tanks, artillery, and large supply pallets. The largest flight system recovered by ADS in the world was the shuttle solid rocket boosters for NASA. This system consisted of a cluster of three 41-meter ribbon parachutes and a typical landed mass of 40 metric tons. The even larger NASA Ares 1X development flight test included a derivative of the SRB system with a cluster of three 46-meter ribbon parachutes. A massive planetary decelerator development program was started in the late 60s that culminated in the Mars Viking disc gap band parachute used for both Viking landers in 1976. 20 years passed before we went to Mars again with the derivative Mars Pathfinder Decelerator in 1997. Using the wealth of data from Viking, modifications were made to the canopy to increase its stability. A similar small-scale development program was completed for the Mars Exploration Rover design, which successfully landed 2 rovers in 2004. Shrinking budgets prompted a return to the Viking-style decelerator configuration, resulting in the successful landing of the Phoenix spacecraft in 2008. Mars Science Laboratory, expected to land in August 2012, also uses a Viking disk band configuration, albeit at significantly increased size. Non-Martian probes have included Venus, Jupiter, and sample return. The Pioneer Venus Large Probe utilized a 5-meter ribbon canopy to separate the probe from its protective aeroshell in 1978. The thick Venusian atmosphere allowed for the release of the parachute at 45 kilometers above the surface. The Galileo probe used a 4-meter ribbon to maintain stability as the probe sampled the Jovian atmosphere in 1995. The Genesis probe was expected to use a modernized version of mid-air retrieval for its recovery system in 2004. Unfortunately, a misplaced acceleration switch prevented deployment of the decelerator system that included a 39 square meter parafoil. The Stardust probe used a 7-meter triconical parachute as its main landing decelerator that successfully returned cometary particles in 2006. NASA's CSBF conducts high-altitude research flights and utilizes a range of decelerators to recover their science payloads. Their flat circular parachutes are sized based on gondola mass with a range from 24 to 46 meters in diameter. These decelerators are not packed, but are strung out as part of the flight train. The canopy apex is released at the end of mission, and the canopy inflates as the system descends. This brief narrative of the long history of aerodynamic decelerator systems has shown the broad and varied utility of these devices. Note the expansive trade space of operational extremes for altitude, speed, and dynamic pressure to date. For stowage volume flexibility and a given package mass, no other technology provides equivalent aerodynamic deceleration. As previously stated, the intent of this lecture series is an informal update to NASA SP 8066. This includes design and modeling details, past project development history, lessons learned, as well as details on modern materials and manufacture. The goal is to provide the viewer sufficient information to be able to ask the right questions and look in the right direction when encountering aerodynamic decelerator systems.